Welcome back to Triptych Algebra. Today we're going to talk about the domain and range of a function. The assumption here is that you've been introduced to functions and function notation, and that you know about independent and dependent variables. The domain is the set of possible independent variable values. In other words, what they are the numbers that may be input into the function. There will be different reasons for why we may not be able to input certain values. For one reason, we might have a mathematical property that does not allow us to input a certain value, or we may have context given a real-world problem. The range is the set of dependent variable values, or in other words, these are the numbers that are output from this function. And you will notice that some functions, for instance, can never output negative numbers or certain positive numbers given the structure of the function. All right, now what we're going to do are look at 4 different examples with the function definition, look at the domain and range, and relate that to the graphical representation of the function. Our first example here is the linear function f of x equals 3x plus 5. In this case, the domain, which are the values that may be input, is actually all real numbers. So in interval notation, that would be negative infinity to infinity. This means we are not restricted by the values that we plug in for x here. And actually, for every linear function, if we don't have an arbitrary domain restriction, the domain is all real numbers and the range is also all real numbers. What this means is that this function, you're allowed to plug in any value you want in for x, and also every value, every real number can be output by this function. The graphical representation of this function shows this domain and the range. As you look at this function, you know this is a line with a slope of 3 and a y-intercept of 5. But as you look as it goes, it will reach every height and depth, or vertically it covers all of the values, the y values we call the output values for this function. And then horizontally, this graph spans all from negative infinity to a positive infinity along the x-axis. By the way, when you're looking at domain and range for a function graphically, the domain is what part of the x-axis is covered by the function. The range is what part of the y-axis is covered by the function. Our next function up is f of x equals x minus 5 squared plus 3. This is a quadratic polynomial function. And actually, with all polynomial functions, the domain is all real numbers. We'll cover more of that later. The range for this quadratic is a bit more interesting. If we look at the graphical representation of this quadratic, which is a parabola, it's an upward-facing parabola. It has a very special point right here. This point is called the vertex. It has an x value of 5 and a y value of 3. Graphically speaking, you'll notice that this graph, as it faces upward, does not cover anything less than an output of 3 right here, or a height of 3. Along the y-axis or the output axis, there's no graph down here. That 3 represents the minimum value that may be output by this function. The range, therefore, for this function is from 3 to infinity. Mathematically, we would know that this is the least value if we analyze these terms up here. This first term, x minus 5 squared, is where I'll be inputting my value. When I subtract 5 and then square that, there is no possible way that this term will end up being negative because the last operation is the squaring right there. Therefore, the smallest thing this term will output before you add 3 is 0. Most likely it's going to be positive. In fact, the only way you're going to get 0 from this is if you plug in an x value of 5. All right, now we have something that has an interesting domain. In this case, our function is f of x equals 3x minus 2. The important issue here is this square root right here. When we are talking about functions of real numbers, we know that we cannot take the square root of a negative. Therefore, this expression right here, the stuff under the radical, this cannot be less than 0. If I plug in a number, for instance, I won't do it, but just imagine here. If I plug in a 0 in for x, 3 times 0 is 0 minus 2. If I plug in 0 in for x, this will give me a negative 2. I can't actually evaluate the square root of negative 2. Therefore, 0 is not a value that I can actually use as an input. It's not in the domain. If we want to find the domain for this function, what we need to do is take this expression, 3x minus 2, and we want it to be strictly greater than or equal to 0. If we solve this inequality for x, we will find the x values that will make sure to output numbers greater than or equal to 0. I'll add 2 to both sides to get 3x is greater than or equal to 2, giving me x is greater than or equal to 2/3. Before I specify the range, if you look at the graphical representation of this function, you will see that it does not extend left on the x-axis or on the input axis beyond this point of x equals 2/3. This graph is not defined for numbers less than 2/3. Even if you plug in 1/2, 0, -5, none of those numbers are in the domain because none of those values are possible inputs. They cannot be input because they will make this expression under the square root negative, and you cannot apply the square root to a negative number. For the range, you'll notice that this function outputs values only greater than 0. This function is not defined down here below the x-axis. It doesn't cover any of the negative part of the y-axis or the output axis. And for that reason, the range of this function is everything greater than 0, including 0. Mathematically, why this occurs is because the square root, again, if we ignore the stuff inside here, the square root never outputs a negative number. It only outputs 0 or positive numbers. Our last example is a rational function, 5 over x plus 4. In fact, rational functions are quite honestly the most interesting functions when talking about domain and range. Before I go about finding the domain for this function, I want to make it clear. Domain being the input values, you should be feeling, hey, I can input whatever I want in for x into this function. And that's true, unless you've previously, because of context or just been told that this function has a domain restriction. You will see that in the near future. You should be feeling I could plug in whatever you want, unless you try to break a mathematical rule when you do that. In this case, the issue is division by 0. So we actually, when talking about domain, are not going to care about what's happening in the numerator at all. All we care about is the issue down here. This expression, x plus 4, cannot be 0. So all we need to do is when we have a rational expression like this, or a fractional expression, we take the denominator, ignore the numerator, take the denominator, set it equal to 0, solve that equation. This solves to x equals -4. Now this is not the domain. This is the one value that is not in the domain. We call this a restricted value. The domain is actually all real numbers except that poor number, -4. In interval notation, it's a bit awkward. We write this as two disjoint sets, -∞ to -4, not including -4, and -4 to infinity. That's how we write the set of numbers that include all real numbers except the number -4. Before we look at the graphical representation of this function, I want to mathematically argue the range. The range, again, are the possible values that are output by this function. Again, you may be thinking, well, what values could I not output by this function? In fact, nearly every single number you can manufacture an output by this by plugging in certain values of x. The only value this will not output is 0. The reason it won't output 0 is because the only way to get a fractional expression equal to 0 is if the numerator is 0. And it's obvious the numerator can never be 0. The numerator is always 5, no matter what I plug in. So the range is actually all real numbers except for 0. All right, now here we have the graphical representation of this rational function, which, by the way, I think is pretty dang rad. Rational functions are really fun, interesting functions, and they have these restrictions and on the domain and often on the range also. You'll notice something weird happening here at x equals -4. There actually is what we would call a vertical asymptote here at x equals -4. This vertical asymptote, this dotted line that I put there, is not part of the graph, but it's kind of a guideline that says that this function never crosses this barrier right here. In the same way, this function has a horizontal asymptote at x equals 0. I'm not going to get into the nitty-gritty of the asymptote conversation right now, but I want to show you that interesting feature to where it looks like this graph is two beautiful graphs, but they're completely separate. And those breaks along the x-axis is at -4, and along the y or the output axis is here at 0. Those are the only restrictions for the domain and the range.